Today we will study inverse kinematics, a motivational example of 2R planar robot. Two revolute joint, this one having length L1 link and this one is having length L2. Suppose this is base frame, here planar robot base frame. So home frame is here x axis, y axis. Here the bigger figure, 2R planar robot having link length L1 and L2. Suppose we want to achieve px comma y. This is x direction and this one y direction. And we want to achieve this point px comma y for end effector. We ignore orientation, but just we want to find the position. How can we achieve this position? So for 2R planar robot here, for this point there are two positions, this one and this one. Here theta 2 is positive, elbow up, and for this one and this one. So this elbow down. One is called lefty and the other is called righty. Here this figure, this one is having length L1, this one is L2. So L1 minus L2, this one. From this to this is L1 minus L2. And from this to this is L1 plus L2. So the workspace for this end effector in this region, from this point to this point, this one. Not inside this, but from this to this, this to this, this to this. Here L1 minus L2 and this one is L1 plus L2. From L1 minus L2 to L1 plus L2. So this is workspace and lefty and righty configuration. This one and this one. This is also in bigger figure. The angle gamma is determined using the two argument arctangent functions. Gamma equal to indirectly tan inverse arctan to y comma x. Observe the figure. From this first link is at an angle theta 1 and the second link is at an angle theta 2 with the link length direction theta 2 in positive direction. So this one is theta 2. Suppose this one is beta. Suppose this one is alpha. This one is theta 1. And from this to this line. This one is L1. This one is L2. And the coordinates of this point x and this point on y direction y. So this is root of x square plus y square from this to this. This one is theta 2. So arctan to gamma is arctan to yx. With these angles, the righty solution to the inverse kinematics for this, referring to figure 6.1b, this one, geometric solution. Angle beta, this one angle, restricted to lie in the interval closer to 0 pi because it is the angle of a triangle. So it must be closed interval belongs to 0 pi. Can be determined by the law of cosines. So here if we apply this for this triangle, this point and this point, cos beta. So L1 square plus L2 square minus this square upon 2L1 L2. So L1 square plus L2 square minus 2L1 L2 beta cos beta equal to x square plus y square. It is the cosine rule for a triangle, from which it follows beta equal to cos inverse of L1 square plus L2 square minus x square minus y square upon 2L1 L2. So this is beta. Because of L1 L2 known, x and y known, so beta is known. Also from the law of cosine for alpha. So alpha is made by this side and this side. So this square plus this square minus this square upon 2 into this into that. So alpha equal to cos inverse this square x square plus y square plus this square L1 square minus L2 square upon 2 into this side into this side, so L1 into root of x square plus y square. So here also x, y, because we want x comma y and L1 L2 known, so alpha is also known. And what about gamma? Tan gamma for this. This is this point, this is y coordinate and this is x coordinate. So tan gamma is y by x, but it is also same as tan inverse of minus y minus x. So common tan inverse function range is closed open interval minus pi by 2 plus pi by 2. But for this opposite quadrant has opposite sign, so it has also gamma same. So we are using arctan 2 functions, a modified domain, closed interval minus pi to plus pi. So from this figure, see here, theta 1 plus alpha is gamma. Theta 1 plus alpha is gamma. And from this, theta 2 plus beta is pi, linear pair. So theta 2 plus beta is pi. So theta 1 is gamma minus alpha. And gamma is known, alpha, beta, gamma known. So we can find theta 1 using gamma minus alpha. And from this, theta 2 is pi minus beta. So here is also known. So to achieve this location, we can find one of the solution theta 1, theta 2, such that we can achieve end-effector position here. By this way also we can achieve this one, but this one angle negative. So I have drawn this another figure. This one is this way and the other one is this way. So here this theta 2, because we are rotating this way clockwise, so angle theta 2 is negative. So minus theta 2 is already negative, so minus theta 2 plus beta for this, and the left solution minus theta 2 plus beta, minus theta 2 plus beta, because theta 2 is already negative because it is in clockwise direction. So minus theta 2 plus beta is pi, and so theta 2 is beta minus pi. And for this one, this angle is theta 1 and this one is gamma. So theta 1 minus gamma, theta 1 minus gamma is this one, which is alpha. So theta 1 minus gamma is alpha, so theta 1 is gamma plus alpha. So for this lefty solution is also derived, theta 1 is gamma plus alpha and theta 2 is beta minus pi. If this one root of x square plus y square lies outside the range closed interval L1 minus L2 comma L1 plus L2, then no solution. And for border point there is only one solution, and between them there are two solutions. For 3-link planar open chains have an infinite number of solutions for points x, y lying in the interior of the workspace. And I am giving the demo for this at the end of video. For 3-link planar open chains, have an infinite number of solutions for points x, y lying in the interior of the workspace. Now the cosine rule. This is the cosine rule. We must study cosine rule using the vectors. See this vector A plus B. Observe the arrow. This is the vector A, arrow is here. This is the vector B, arrow is here and the tail is here. So A plus B equal to C. Triangle law for vector addition. Parallelogram law also, triangle law for vector addition. Suppose this angle is gamma, but here this vector the tail is here and this vector is tail is here. So angle between two vectors, if you put a vector here, the angle between them is called pi minus gamma, not gamma. Gamma is the angle of triangle, but pi minus gamma is the angle between vector A and B. So A plus B equal to C. So vector addition, mod C, result vector of 2, mod C equal to A square plus B square plus 2AB cos of angle between two vector, which is pi minus gamma. So C is root of A square plus B square, but pi minus gamma is minus cos gamma. So minus 2AB cos gamma, because of cos pi minus theta is minus cos theta. So squaring this, C square equal to A square plus B square minus 2AB cos gamma. Subtracting cos gamma is A square plus B square minus C square by 2AB. how cos of pi minus theta is minus cos theta? See here, unit circle. For theta corresponding point theta is P, and corresponding to pi minus theta is Q. For this coordinate x comma y, then for this coordinate of minus x comma y. So x went opposite. So cos of pi minus theta is minus cos theta. So using this, we have used this cosine rule here in our this. Okay. For 3R planar robot, if you want to achieve Px comma y for this end effector, this one, this point, say the dark point, there are 3 links, 1, 2 and 3. One of the solution is this. Symmetric, another solution. See, this way, symmetric. This one, the link here, then this one and this one. Now I am changing this one, I am changing. Just a minute. This is another. Now if you want to rotate this one, now I want to achieve this, so I will rotate this joint. See here, we can achieve this one. Again, for another solution, this is the origin home frame. Now we can achieve same point again, this one. So for 3R planar robot, there are infinite ways to achieve this point. For 3R planar robot, see this one. Now this is another solution, and this way also, keeping these three constant straight line, I am adjusting. See, these 2 links are in a straight line, so then also we can achieve this point. So there are infinite number of ways to achieve Px comma y if it is in the range for 3R planar robot. And for 2R planar robot, if it is in the range, if either one position, it is at boundary location, or in between them there are 2 possibilities. If we require only position, not orientation. Okay.